Hey everyone, welcome to The Explainer. I am so thrilled to have you here with us today. We are going to tackle one of the most, honestly, foundational debates in modern data systems architecture, and that is distributed versus single-node systems. We'll be exploring the fascinating trade-offs between microservices, serverless deployments, standard cloud computing, and even supercomputing. If you're looking for a structured, deeply informative breakdown of how the world's most data-intensive applications are designed and the true price of scaling them, you are in exactly the right place. Okay, let's dive right into this. To kick things off, let's start with a wonderfully simple question. Why not just use one giant computer for everything? I mean, it is incredibly tempting, right? When you write code on a single machine, it generally behaves in a predictable, deterministic way. That means if the hardware is functioning properly, giving the system the exact same input will always produce the exact same output. It's a highly reliable, super easy to understand baseline. You don't have to worry about your data getting lost on a wire somewhere out in the ether. Yet, the entire tech industry seems completely obsessed with splitting things apart into dozens, hundreds, or even thousands of pieces. So why is that? Here is our roadmap for today. First, we'll look at the single-node baseline. Then exactly why you distribute your system, followed by a distributed reality check. After that, we'll touch on microservices and serverless, compare the cloud with supercomputing, and finally wrap up with the final trade-off. All right, Section 1, the single-node baseline, the power of one. So a single-node system simply means your task is performed entirely on one isolated machine. But what's absolutely vital to understand here is just how incredibly capable this setup has become today. It is often far simpler, significantly cheaper, and vastly more predictable than a distributed setup. I mean, today's hardware has grown to astronomical proportions. We've got CPUs with dozens of cores, servers packing terabytes of raw memory, and lightning-fast solid-state storage. When you combine that immense physical hardware with highly optimized single-node databases, think DuckDB, SQLite, or KuzuDB, an enormous number of workloads can run flawlessly on just one box. By keeping your data processing local, reading and writing straight from local memory, you operate at lightning speed. And more importantly, you completely avoid the unpredictable nature of an external network. Passing a memory pointer locally is infinitesimally faster than serializing data, shoving it across a network cable, and deserializing it on the other side. So for a vast majority of applications, keeping it on one box is literally the most pragmatic, cost-effective choice you can make. Moving right along to Section 2, why distribute your system? The push for scale. According to our source material, there are 8 core reasons that virtually force an architecture to span multiple machines, pulling us completely away from that comfortable single-node baseline. Let's quickly unpack these. Number 1, inherent distribution. If you have end users interacting from their mobile phones and laptops all over the world, well, your system is already unavoidably distributed by its very nature. 2, requests between cloud services. If your data lives in one managed cloud service but gets processed in a completely different compute instance, that data has to cross a network boundary. 3, fault tolerance. You want high availability. If the power goes out in one specific data center building, you absolutely need redundancy so your app seamlessly fails over to another building and stays online. 4, scalability. Eventually, your data volume or processing load is going to outgrow the physical limits of the largest single machine you can possibly buy. 5, latency. We are all limited by the speed of light. You want web servers physically located close to your users, say in Tokyo for Japanese users, so network packets don't have to travel halfway around the globe to Virginia just to fetch a simple web page. 6, elasticity. This is the ability to automatically scale cloud instances up for peak traffic, like a massive Black Friday sale, and scale them back down on a quiet Tuesday so you only pay for what you actually use. 7, specialized hardware. An object storage system might need machines packed with massive, dense hard drives, while a machine learning system needs machines packed with specialized GPUs. You just have to distribute to match the hardware to the task. And finally, 8, legal compliance. Strict data residency laws, like GDPR in Europe, often legally dictate that personal data about citizens must be stored geographically and physically within that country's sovereign borders. Which brings us to Section 3, the distributed reality check, the price we pay. Now for the reality check. And spoiler alert, the reality of distributed systems is incredibly complex and, honestly, pretty messy. The absolute biggest headache you introduce is non-deterministic partial failures. Think of it this way. A single computer is kind of like a bicycle. It either works or it completely falls over and stops. Over a network, a distributed system is more like a fleet of vehicles. The engine might work perfectly on one truck, but the steering wheel falls off another, and a third runs entirely out of gas. Part of your system might be completely broken while the rest is totally fine. When you send a network request and get a timeout, it is entirely non-deterministic. Did the receiving service crash? Was the network cable severed? Did the service successfully process your request, but the return message just got lost on the way back? You simply don't know. Plus, even on the absolute fastest, state-of-the-art data center networks, making a cross-network call is thousands of times slower than calling a function directly in the same local memory space. And we definitely can't forget about data consistency. When every individual microservice has its own independent database, maintaining logical consistency across all of them becomes an application developer's worst nightmare. Because robust distributed transactions are notoriously slow and rarely used at high scale, you are constantly dealing with race conditions and temporarily stale data. Because of all those partial failures we just talked about, troubleshooting this kind of architecture is incredibly difficult. Imagine a single user clicking a checkout button on a website. That one single click might silently trigger 50 different backend microservices, one for inventory, one for billing, one for shipping, one for the confirmation email. If the user's screen hangs for 5 seconds, where exactly is the bottleneck? Which specific service out of the 50 was the slow one? You can't just attach a local code debugger anymore. You need digital detectives. And this is exactly where observability comes in. Tools like OpenTelemetry, Zipkin, and Jaeger are absolutely essential here. They let engineers trace the entire path of a request, showing exactly which client called which server for what specific operation, and exactly how many milliseconds each individual network hop took, just so you can figure out what went wrong in that massive spiderweb of requests. Okay, Section 4. Microservices and serverless, managing the chaos. So how do modern organizations attempt to wrangle all this complexity? Well, the most common approach is the microservices architecture. This practice involves deliberately decomposing a massive monolithic application into multiple, much smaller, interacting services. Each individual service has one extremely well-defined purpose, it exposes an API to clients over the network, and it's maintained by a completely independent engineering team. Now, the huge, undeniable advantage here is independent updates and targeted resource scaling. You can deploy a fix to the billing service without having to reboot the entire application, but it heavily breeds new complexities. Evolving those APIs becomes a delicate, high-stakes dance. Because you cannot simultaneously update a server and instantly force an update on every single client application relying on it globally, maintaining strict forward and backward compatibility is notoriously difficult. If you change a simple data field name, you might accidentally break thousands of downstream processes that were expecting the old format. This brings up one of my absolute favorite insights from the source material. Microservices are primarily a technical solution to a people problem. That really hits the nail on the head. The fundamental reason microservices exist is organizational scaling. If you have a massive tech company with 5,000 engineers, they literally cannot all coordinate pushing code to one single codebase simultaneously without stepping on each other's toes in endless coordination meetings. Microservices effectively decouple the teams, allowing them to progress independently. But the inverse is also true. If you're in a small startup with only 5 engineers, prematurely adopting a complex microservices architecture is likely just massive, unnecessary technical overhead. In that scenario, you're much better off building the application in the simplest, most monolithic way possible. Now, if managing massive fleets of microservice virtual machines sounds exhausting to you, the industry does offer another path: serverless, or function as a service. In this model, you essentially outsource the entire infrastructure management headache right over to the cloud vendor. You don't do capacity planning, you don't provision or patch operating systems. The cloud provider automatically allocates compute resources on the fly based on incoming user requests, and you are billed strictly on metered code execution time, often down to the millisecond. It sounds like magic, but to offer this, cloud vendors are forced to impose strict limitations. They put maximum time limits on how long your function is legally allowed to run before it just gets killed. They severely restrict the back-end runtime environments, and you might frequently suffer from what engineers call cold starts. A cold start is this highly noticeable delay that happens when a serverless function is woken up to handle a request for the very first time after a period of inactivity. The underlying infrastructure literally has to boot up an isolated container before your code can even begin to execute. Let's pivot a bit for Section 5, Cloud versus Supercomputing, different scales, different rules. Let's actually look at what these massive systems are crunching on a daily basis. Standard cloud computing is heavily optimized for online services. It handles highly interactive user requests, fetching real-time business data, processing e-commerce transactions, and keeping front-end web apps running smoothly. Supercomputing, by stark contrast, is built from the ground up for computationally intensive batch jobs. We're talking about predicting global weather patterns, modeling long-term climate change, or simulating dense molecular dynamics. These jobs might run continuously for days or weeks. They are just fundamentally different types of computational work. And because the fundamental nature of the work is so different, how these systems handle faults is basically night and day. In the cloud, your system must be highly available and always on. It absolutely has to survive those partial network failures seamlessly because it needs to continually serve human users with minimal interruptions. Stopping a major cloud web service for an hour to fix a server would literally be front-page news. But in supercomputing, if a single processing node fails during a massive 2-week batch job, a completely common and acceptable solution is to simply stop the entire cluster's workload, physically repair the faulty node, and then restart the massive computation from the exact moment the system last checkpointed its state. Because scientific batch jobs aren't interacting with live, impatient web users, pausing the entire cluster for an hour to swap a bad motherboard simply doesn't ruin the user experience. Their underlying network setups are totally different too. Supercomputers are usually physically located in a single, massive, climate-controlled room. The nodes are geographically extremely close to each other. They use highly specialized multidimensional network meshes and communicate via RDMA, that's Remote Direct Memory Access. RDMA is this incredible tech that literally allows one computer to access another computer's memory directly over the network, completely bypassing the operating system kernel for the maximum possible speed. They can do this because they assume a very high level of security and trust within that single laboratory environment. Contrast that with the cloud. The cloud is heavily multi-tenant. It's exactly like an apartment building, where dozens of completely mutually untrusting organizations are sharing the exact same physical hardware and network switches. This multi-tenant reality forces the public cloud to rely heavily on standard IP and Ethernet, alongside incredibly strong resource virtualization, constant encryption, and rigorous authentication. And all of that inherently adds processing latency that supercomputers deliberately avoid. All right, bringing it all together with Section 6, the final trade-off, choosing your path. Let's go back to this core idea. Performing a task on a single machine is often much simpler and cheaper than setting up a distributed system. We have deeply explored the incredible necessity of horizontal scaling, the organizational requirements of microservices for sprawling engineering teams, and the global reach of modern cloud computing compared to specialized supercomputers. But we've also unpacked the massive, sobering reality of that complexity, the non-deterministic network faults, the painstaking necessity of tracing distributed requests, and the ongoing nightmare of data consistency. If you can possibly avoid opening that Pandora's box of distributed chaos by keeping your architecture contained on a single, highly optimized, wildly powerful modern machine, it is almost always worth doing so. So, as you look at your own engineering projects and application architectures, I want you to ask yourself, does your specific use case truly require a complex distributed system? Do you honestly have the human scale people problem that microservices are specifically meant to solve? Or would a single, modern, highly optimized node actually suffice? Sometimes the absolute most elegant and sophisticated engineering decision you can make is actively choosing the simpler path. Thank you so much for joining me on this explainer. Keep questioning those foundational assumptions, keep building, and I'll see you next time.